So continuity over an interval. The definition for continuity over an interval says that a function is continuous on an interval if the function is continuous at each point in the interval. So you can already see sort of the interrelatedness of the continuity on an interval and continuity at a point. So what we need to know first is that the following functions are continuous on all points in their domain. And so there's a list of functions here, and I'm just going to kind of give you an example of what some of these look like. Polynomial, these are things like quadratics, x squared plus 2x minus 1, or it could be something like x to the 5th minus 2x squared, something like that. A cubic, a quadratic, a quartic, anything just raised to a power, those are our polynomials. A rational function is going to be something where you have a variable in the denominator. So the most simple one that we ever deal with is like 1 over x, but it could be something like 2 minus x over x squared plus 2x plus 3. That would also be rational. Power functions, I find these slightly confusing because power functions are kind of like polynomials. So something like x to the 3rd, that is a power function. But the different types of functions that we're going to see come in that are different than this are going to be like if I had x to the 1/2 power. And if I had x to the 1/2 power, what is that really? What's another way that we could write that? It's the square root of x. So this would include any type of root problem that you might have. So you might even just want to write that roots are included here. It also could include something like an x to the negative 2 power, which actually becomes more like a rational. So power functions, I don't love that category because it overlaps with some of the other categories there as well. And I don't like my categories to overlap. Exponential, that is anything that's going to have a variable in the exponent. So it could be something like 2 to the x power. It could be something like e to the 3x minus 1. Those are exponential equations. Logarithmic, this of course would be like log base 4 of x. It could be the natural log, something like x minus 3. It could be just the common log, so log of x squared. Those would all, of course, be logarithmic. And then trig functions, you guys are familiar with. I'm not going to list those out, but that's your sine, cosine, tangent, cosecant, secant, and cotangent. So these types of functions are continuous for all points in their domains. So it's important for us to know the domains for these different functions to help us see what type of continuity we're going to have. Because if we have something that is not in the domain of that function, then that function is not going to be continuous at that point. So domain, of course, is your possible x values. And they're super easy for polynomial functions. Your domain is all real numbers. have used that R with the double bar with you guys before, I think, to mean all real numbers. Okay, for your rational functions, the denominator cannot equal 0. Okay. Power functions, again, I don't love this category because it includes a lot of different things. Something like a cubic function doesn't have any restrictions on its domain. A quadratic doesn't have any restrictions because those are actually polynomials. If we had x to the negative 2, that kind of makes it rational, which means the denominator cannot equal 0. The main thing I want to focus on here is for roots. And actually, I guess I should say even roots. For even roots, the radicand, oh, that's a fancy word, is greater than or equal to 0. Radicand is a fancy word that means whatever is underneath the square root. So, for example, if I have x plus square root of x plus 2, then my radicand is x plus 2. So, for my domain, I would have to have x plus 2 would have to be greater than or equal to 0. Or, if I move the 2 over, x is greater than or equal to negative 2. There, so that's an example. Now, this only happens with even roots, so a square root, a fourth root, a sixth root. Odd roots, you can take a cube root of a negative number, so it does not have any restrictions on its domain. Okay. Exponential functions are also pretty easy. They are going to be all real numbers. And then our last one, logarithmic. Whatever you're taking the log of, there might be a fancy word for that too, but I don't know if there is. So, whatever you are taking the log of must be greater than 0. And greater than, not greater than or equal to, you cannot take the log of you cannot take the log of 0. And then the last one, we're going to list these separately. Sine is all real numbers. Cosine is all real numbers. And then for tangent, we'll recall, I'm going to just go ahead and write this. Tangent is sine over cosine. So cosine of x cannot equal 0. cosecant is 1 over cosine. So, again, cosine of x cannot equal 0. Cosecant is 1 over sine. So, sine of x cannot equal 0. And cotangent is cosine over sine. So, sine of x cannot equal 0. Okay, so let's look at what some problems are going to look like for this. Example 1 says, show that f of x equals 1 over x minus 1 is continuous on the interval from -2 to infinity. So, for this particular function, we have a rational function. Rational functions are continuous on their entire domain. So, we just have to look for the domain of this particular rational function. So with a rational function, how do I tell what is not part of the domain? What's going to give us problems with the domain? 1. That's the only thing, right? I can't have 1 because it's going to give me a 0 in the denominator. So my domain for this is x cannot equal 1. So x right there. X cannot equal 1. And is 1 in the interval from 2 to infinity? It is not. It's below 2, right? So, we could say that f of x is continuous on the interval from 2 to infinity because what type of discontinuity am I going to have at x equals 1? Okay? It's not a hole. Holes cancel with something in the top, and nothing is there to cancel with. So, vertical asymptote. Because the function has I'm going to be lazy here, vertical asymptote at x equals 1, but 1 is not on the interval. Thank you. From 2 to infinity. And there's other ways you can say this. Don't think that this is the only way that you can phrase this. You could say something about the domain of this function is everywhere that x does not equal 1. 1 is not on the interval from 2 to infinity, so it's continuous on this interval. Any questions? All Alright, so we have this graph here below. The graph is made up of a line, segment, a point, and part of a parabola. Is g of x continuous on the interval from 4 to 8? Okay. So as we look at this graph, we are only looking from 4 to 8. So if I put in some dotted lines here, got one here at 4 and up to 8. So from 4 to 8, Liliana, do we have any discontinuities in that range? We do not. Now, if it had been somewhere else, we would. The interval from 4 to 8. Oh, this is some crazy stuff. The graph is a continuous parabola. And it told us here that it was a parabola, so we know that that's a continuous function. So I have continuity here. I didn't ask. Oh wait. So yes, I did ask another question. I just can't see it because okay. If we change that question and make it from -2 to 8, so -2 is right here, Destiny, is that function continuous from -2 to 8? It is not. Where does it have a discontinuity, Destiny? 3. So we would say for this, to prove that there is a discontinuity there, we would say, in this particular case, what's the problem there with that discontinuity, Destiny? Why is it not continuous? Okay, so it's kind of, depending on, connected is not like a math word. So yes, it is, that's kind of true, but whenever we're trying to prove something is continuous, we had 3 things that we had to show. We had to show that f of, in this case, 3 exists. Okay, so does f of 3 exist? Okay, what is it? It's 1. Very good. So f of 3 exists, and it's 1. So that's okay. We also have to show that the limit as x approaches 3 of f of x has to exist. Does the limit exist here? Okay, what is our limit? It would be -3. Perfect. So we have the function exists, we have the limit exists, but the third thing is that those two have to be equal to each other. And do they equal each other? They do not. So we would say on this, we would say no, because at x equals 3, f of 3 does not equal the limit as x approaches 3 of f of x. So whenever you're thinking of continuity, you've got those 3 things that have to be proven. If you have something like the first one, from 4 to 8, there were no problems. So you can just say that what type of graph it is continuous on all those intervals. We didn't even have anything to really test right there because there were no possible points of discontinuity. But for whenever you do have a point of discontinuity, think of those 3 things. You have to have f of c exists, limit as x approaches c of f of x exists, and they have to equal each other. So think of which one of those is not true, and that'll be your reason for those. Okay, questions? Destiny did good with that graph problem. She's getting better. Why is it? What's it doing? Oh no. It's probably going to skip. Okay. Alright, so here we have, is f of g of x continuous on the interval from negative infinity to infinity? So we're talking about all real numbers here. So in order to look at f of g of x, we first need to just find what f of g of x is. So we would have f of g of x is going to equal, we're going to take g of x and replace the x right here. So we'll have the square root of x plus 2 minus 5. Okay, so this particular function has a lot of problems with it. So I'm going to look at both of them, although just one will be fine to answer this question. Is it continuous? Because that's a yes or no question. So in this function, we have both the square root and we have variables in the denominator. So the square, what's underneath the square root, the radicand, has to be greater than or equal to 0 for that domain of that function. So for this particular case, we would have to say that x plus 2 has to be greater than or equal to 0. And so that tells us that x has to be greater than or equal to negative 2. So this is part of our domain here. So right away, we know that this is not going to be continuous because x has to be greater than or equal to negative 2. If I try to plug negative 5 into this equation, I'm going to get negative under the square root, which is not real, so which is imaginary, so we can't deal with that. The other thing that we have to watch out here for is that we can't have zeros in the denominator, so that denominator, square root of x plus 2 minus 5, the whole thing cannot equal 0. So that means that the square root of x plus 2 cannot equal 5. We could square both sides. X plus 2 cannot equal 25. And we could subtract that 2. X cannot equal 23. So in this case, we've got two restrictions on our domain. We could say the domain of f of g of x is, I'm going to write it this way. Sometimes you'll see it written like this, x, and then you'll see a bar, and that means x such that x is greater than or equal to negative 2, and x does not equal 23. So that notation might be a little weird to you. This right here, that bar right there, means such that. And this upside down U right here, we use this in Math 2 some, I think, means and. The other way, I'm going to go ahead and write it the other way. You also could use interval notation for this. You could say that the domain is your lowest possible value is negative 2 up to 23. but I would use a parentheses for that. And then from 23 to infinity. So you could exclude that value at 23 by using those parentheses there. And so since this is the domain, we can say so f of g of x is not continuous for negative infinity to positive infinity. Okay, questions? All right. Alright, so here we have a piecewise function. This is kind of a weird piecewise function. It's also going to lead into the next thing that we're going to do. I went ahead and gave you that other set of notes as well. In this case, we got this piecewise function, and a lot of times our piecewise functions are for like x is less than or equal to 3 and x is greater than or equal to or greater than 3. But here, x squared minus 9 over x minus 3 is defined for everywhere except x equals 3. So this is, you can, whenever we see this right here, x does not equal 3, this means everywhere except x equals 3. So that right there should be making us think that we've just got a hole in the graph somewhere, probably, more than likely, anyway. And then this 3, it's 3 at 3. This is just a point, a single point that we have. Single point that we'll have here. So when I look at this, this is defined everywhere except for x equals 3, and I can see probably why it's not defined at x equals 3, because if I plug 3 in, I'll get 0 over 0. So what we can do here to find whether or not this is continuous is, this is a rational function. It's going to be continuous everywhere except for at x equals 3 because of the 0 in the denominator. But if this continuity is a hole that is filled in by this point, then it would be continuous. So what we can do is we can take the limit as x approaches 3 of x squared minus 9 over x minus 3. And so if we take that limit, if you plug in 3, you get 0 over 0. So let's factor x plus 3, x minus 3, all over x minus 3. And our x minus 3 is canceled. So then we can just plug in our 3, and we get 3 plus 3 equals 6. So the limit as x approaches 3 of this top equation is 6. The value at the point is 3. So whenever we think of what this is going to look like, actually let's just go graph it in Desmos really quickly. We're going to have x squared minus 9 over x minus 3. When we graph it, it just looks like a line, but if we look at 3, if I can get it to that point, right there at 3, it went away immediately, but right there at 3, we have an undefined point. So what we really got there is just a hole in the graph. But our extra point is at 3, 3, not at 3, 6. So is this going to be continuous at 3? It is not. So what we've got there is a lot like that one that we had on the graph. We've got a hole in the graph, and then we've got a point down below it. So, so this is not continuous at 3. So you could say the f of x is continuous for, I'll use that same x such that x does not equal 3. Or, if you use interval notation, you could say it's continuous from negative infinity up to 3 and 3 to infinity. So by using those parentheses right there, you exclude the 3. All right, questions. All right, we're going to go ahead and take the next set of notes also, because we kind of got a little bit off. So I pass those out to you. Let me save this. So you'll see here we've got a problem that looks a lot like the one that we just did. It's just the instructions are a little bit different. So we've got f of x equals this equation here for x not equal to negative 2 and k for x equals negative 2. So this is, whenever we see x does not equal 2, that tells us that we're talking about everywhere except x equals negative 2. So we're looking at this graph. It's basically, this is our graph all the time, but we're going to have this one little point, and we want it to fill in what hopefully is a hole in the graph right here, because vertical asymptote cannot be removed. So, so in this case, since I'm looking at this function all the time except for at negative 2, I want to do the limit as x approaches negative 2 of x squared minus 4 over x plus 2. And x squared minus 4 will factor, so I'm going to go ahead and factor it into x plus 2 times x minus 2 over x plus 2. And then our x plus 2's can cancel. So we will get negative 2 minus 2. So we will get negative 4. So if k equals negative 4, then that point will fill in the whole of our graph. In a lot of ways, this is just a different way of asking a limit problem whenever you see something like this. Okay, questions? Okay, so if we look at example 2, it's a lot the same. You will see here that the domain for this is x is greater than or equal to negative 20. X does not equal negative 4. Why did they have to put that x is greater than or equal to negative 20? The square root. If you plugged in negative 30, you would get an I for this. So we can't use any values lower than that. So this is still saying that we use this equation everywhere except for x equals negative 4 as long as our values are bigger than negative 20. Because if they're not, this equation doesn't exist at all. So we're still really doing the same thing here. So we're going to do the limit as x approaches approaches negative 4 of the square root of x plus 20 minus 4 over x plus 4. And Wendy, what are we going to have to do to solve that? Yes, so we will have that conjugate of our square root expression, so x plus 20 plus 4 on top, and x plus 20, square root of x plus 20 plus 4 on the bottom as well. And when we do that, we're going to have square root of x plus 20 times square root of x plus 20 is x plus 20. The middle terms are going to cancel, and then we got to do negative 4 times positive 4, so we get negative 16 over x plus 4 times the square root of x plus 20 plus 4. And x plus 20 minus 16 gives you x plus 4. So is it okay with you guys if I just go ahead and mark those out instead of rewriting that? Because this will be x plus 4. So now we just have the limit as x approaches negative 4 of 1 over the square root of x plus 20 plus 4. If I plug in negative 20, I've got 1 over the square root of negative 20 plus 20 plus 4. Negative 20 plus 20, of course, is 0. So we're going to get 1/4 for our answer here. I don't know why I plugged in 20. I think I was looking at this right here. Don't plug in 20. Plug in negative 4. You're going to get a different answer. Yeah, so, yeah, don't do that. Do this instead. So, negative 4 plus 20 plus 4 will give you 1 over 4 plus 4, which will give you 1/8 there, and that looks better. Thank you, Hannah. All right, questions? All right. Okay, here's our next one. They give us this equation. It says, for what value of c is the function defined by this equation continuous at x equals negative 1? So, first of all, if we're just looking at x equals negative 1, we're only really using 2 pieces of that piecewise function. So, Harper, which 2 pieces are we using? The top, the middle, or the bottom? Okay, the middle and which other one? Top. Okay, so those 2 are the ones we're looking at here. The bottom really doesn't matter at all for this question. So if we're looking at negative 1, that means x is replaced with a negative 1. So I would have negative 1 whenever I plug into this top equation. And that has to equal what I get if I plug negative 1 into the second equation. So be careful with all these negatives here. You'll have negative 1 squared plus negative 1 plus c. The c there that we can't replace, but that's the variable we want to solve for. So negative 1 is going to be 1. What do I get right here when I do negative 1 squared? It's going to be negative 1. We square first, which makes that positive 1, but we still have this negative out here, so it's going to be negative 1. If you multiply first and then square, you'll get a positive, so be careful there. And then we've got like a minus 1 plus c. So 1 equals negative 2 plus c. If we add our 3, add our 2, 3 is going to equal our c. Okay, questions there? All right, let's do a couple crazier ones. This one we'll need our calculator for. Let me just go ahead and open this up. All right, so this tells us the function is continuous for all real numbers. That should say find the values, possibly only one, possibly more, of a. So, in this particular case, x is 3 is the place where these two are going to come together. So I would plug 3 into both of these equations and set them equal to each other. So I would have e to the a times 3, which I'm going to write 3a, has to equal 2 times 3 plus a. Remember, whenever you're doing this, the x is always the variable that gets replaced. So here we've got e to the 3a equals 6 plus a. And we don't know how to solve that. And I don't know that there is a way to solve it by hand. If there is, I'm not familiar with it. So, if you get something like this, it's going to be calculator active. So if you look at your calculator, there's a good reason we don't let you guys use these calculators whenever you're in lower level math, because watch what it will do. This is crazy. You're going to pick F2, which is algebra, and then number 1 there is solve. Okay, so I'm just going to type into the equation. I am going to use an X instead of the A just because it's easier to type, but it will still solve it if you type it in with an A. So you could do it that way if you wanted. So e to the 3x, and you got an equal sign is right here, sort of catty-corner to that 7, 6 plus x. Now, so you type in your equation, then you do have to put a comma and an x before you finish your parentheses there. So you're going to do solve. You're going to do solve. Whatever the equation is, comma x, and then close the parentheses. Is how you do this on the calculator. And if you got it typed in correctly, you're going to hit enter. It is going to take it just a second to figure this out. And you'll also see that warning, more solutions may exist. So, so we get the answers, x equals 6.6305. Everything you do in AP Calculus, if you're giving me a decimal, you need to have at least 3 correct decimal places. So, like, you could have for this 0.631. Or you can just keep all the decimal places. It really doesn't matter. You just have to be correct 2, 3 decimal places, and that'll be the case on the exam as well. So you'll have x equals 0.631. Our other one that it gives us is just -6. I don't think it's actually -6. I think it rounded that. And if you scroll over, you also get another -6. So what that tells me is that it probably was like -6.00000001, and the other one might have been like -5.999999. So they've rounded both of those, so they might have actually been separate ones. But for our purposes, we only have to be correct to 3 decimal places, so let's just put -6 one time for this particular problem. So you would have 2 answers that could make this correct here. And you can always check by plugging the numbers back in. So if we do if we do e to the, let's just use the -6 to check for right now. So it'd be -6 times 3. There we would get e to the -18. If we do 2, let's see, hold on. Right there I really don't want e to the -18. I want to do the green button enter. Wait. Green button enter so that it actually gives me a decimal. And then if I did 2 times 3 minus 6, I would get 0. But this is essentially 0 because it's 1.523 e to the -8. You have to move the decimal place 8 places backwards, so it'd be like 0.7 zeros and then 1523. So they're within 3 decimal places. We're close enough to each other there. You could try it with the 0.631 also just to check, but we'll leave it where it is right now. Questions on that one? So on your homework, you will, I think homework, most of these are going to be non-calculator, but I need to look back over them to be sure about that. Okay, example 5, this one is non-calculator. We need to know what value of b, if any, will make this continuous at 1. So I've got this equation, and I need to know what values of b are going to make this equal to, or make this continuous. Notice that this one's split up a little bit differently. I've got this quadratic for whenever x is less than 1. I've got this rational function when x is greater than 1. But I've got this point whenever x equals 1. So that tells me that this has to equal negative, like either one of these have to equal -1. Because if our f of 1 does not equal the limit at 1, then it doesn't matter if they equal each other. So if you didn't have this, these two would be very difficult to set equal to each other. You'd probably definitely be calculator active. But since this equals -1, we can do this problem without a calculator. So we could say b minus b times 1 is the number we're plugging in here, minus 1 squared, has to equal that -1. And so that is b minus b minus 1 equals -1. And then b minus b just cancels, and we get all real numbers. -1 always equals -1. So I'm pretty sure we can't say b equals all real numbers. But let's just go do the other part first and see what we think about that. So if I have 3 over 1 minus 4/7 minus b, that is going to equal -1. And so 1 minus 4/7 is going to give me 3/7, so I'm going to have 3 over 3/7 right there. I'm going to do this part over to the side. And then dividing fractions is easy as pie. We're going to flip the second and multiply. And so that's like 3 over 1 times 7 over 3. 3's will cancel. We're just going to get 7 whenever we do all of this stuff right here. So 7 minus b equals -1. And so we could subtract 7. So negative b equals -8. And so b will equal +8. So this one was a little bit weird because b equals 8 here and all real numbers here. If you got b equals 8 here and b equals 4 here, that would tell you there's no number that will work. But since this could be, what we learned here is that b could be any number here, and you would still get -1. So since it can be any number, the number we want to choose is 8. So if we pick 8, our b can be 8 here. All right, questions? All right, notes are a little long today. They will not be quite as long the rest of the week. Homework is going to sound terrible when I write it down, and that is because I've listed a lot of the problems separately. It's 26 problems. The first 6 are just graphs to look at, so it's not nearly as bad as it looks. So as I write it down, don't panic. You're going to be on page 96. And 1 through 6, these are graphs here. 7 through 15 odd. 17, 18, 29, 30, 32, 33 through 36, 64, 66, and 77 through 83 odd. So, 1 through 6 are graphs there. Hold on. 7 through 15 are one-sided limits that really went with the work before, but we didn't do it. You got several one-sided limits. 30 and 32 have graphs. You're looking at continuity on an interval for 33 through 36. 64 and 66 are going to be that removing the discontinuities. And 77 through 83 odd. Those are just telling where your discontinuities are at.